This code is Qz0711Spg15. And is intro to chem equations. And when we, of course, introduce the chemical equation, most of you are familiar with the idea of chemical equations, and you know about reactants and products such as that, and the symbology in general consists of elements and compounds, symbologies, balanced equations. A lot of this you already know, okay? And it's my job to reinforce that and then add to it, primarily in the stoichiometric. What can you calculate from a chemical equation? That is a revelation to most students. Just looking at a chemical equation is one thing, and having an understanding, yeah, that's the formula for making water. But using the chemical equation to derive quantitative outcomes is not as visible to most students as you may need. Let's see. Okay. So, number one, a reaction conforms to the conservation of matter when the number of reactant compounds equals the number of product compounds. All right, and law the statement is the number of reactant compounds equals the number of product compounds. To some, this is a misconception. In the context that I placed it, this is not true. Okay? Some reactions will have a couple of reagents on the left side and one on the right side. The one we are very familiar with is the synthesis of water from basic elements in standard state. So reactions frequently they may have two components on the left and two components on the right. That's an outcome circumstantially of the reactive process. But when you run into a chemical reaction, one of the issues in mass balance, or the law of conservation of matter, is that you have a conservation of matter, not a conservation of number of particles in terms of molecules. Now you'll have a conservation of elements in that you'll have X number of oxygens on the reactant side and X number of oxygens on the product side, but they may be embedded within a new compound. So that would condense the number of particles down to one, and that would be a compound like that. So this is not true. So you want to be aware of that. Okay? All components are written correctly with respect to oxidation states. The sum of all charges in each compound equals 0. Let's see. That is 100% true statement. But what's the fallacy? It is not a mass issue. The question asked you for conservation of matter. So what has to conform to conservation of matter? It's the law of mass balance. So you have to have the total weight of the reactants equal total weight of the products after reaction. To have all the proper compounds written in the correct oxidation states, that's fine. But if the mass doesn't balance, you don't have a proper chemical equation. Sodium chloride, plus lead nitrate. These are all in water. Goes to lead. I'm going to put sodium nitrate first. Sodium nitrate aqueous plus lead chloride will precipitate. We'll talk about that shortly. In writing this notation, all of the substances are written correctly. The sum of the charges are balanced. But does that conform to the law of conservation of matter, which was the object of this problem? No, it does not conform to the law of conservation of matter. You may have compounds, but I have 2 nitrates here, and listed on the product side I only have 1, and I have to balance that by applying a coefficient. Okay, so when we talk about balancing an equation, there are a few things that have to be taken into account. Not just mass, but also charge balance. And I wrote the question backwards. Charge is true, but we didn't balance it by mass. So we have to increase the number of chlorides. Sum of the mass of reactants, I assume they're written correctly, equals sum mass of products. Is that true? Yes. It's absolutely true. That is the law of mass balance. Matter is neither created nor destroyed. It's only changed in form. Okay. Simple example: hydrogen's a gas, oxygen's a gas, and typically water. You can have water vapor as a gas, but we know of water as a liquid for the most part. Okay. All right. This is just a rudimentary issue that you need to be aware of. The last one. None of the above conform to the law of conservation of matter. Well, since this one does, that is an invalid. But for any equation, 1, you must have a conservation of mass, a conservation of charge, and 3, we haven't emphasized much, I've mentioned it, conservation of energy. The intrinsic energy content of products may be less than the intrinsic content of reactants. What's the difference? Heat loss or heat gain. So the conforming to the conservation of energy takes into account in the process gaining or losing energy, net changes. So that gain of energy accounts for the conservation or loss of energy, accounts for the conservation of energy. But in any chemical process, You got, and I think you appreciate the balance, mass balance, but also develop an appreciation for charge balance and energy balance. And we'll develop these more as we get to them in more detail. But it's good that you know there's not just mass balance that characterizes a chemical equation. Reactions whose constituent elements undergo a change in oxidation state are generally referred to as what? Okay. Reaction elements undergo a change in oxidation state. There are two classes of reactions that we are going to be familiar with, focusing on. One class of reactions is an oxidation reduction. And another class will be a double replacement, as some people call it, but it is typically referred to as a metathesis. In going from reactants to products, if you're dealing with an oxidation reduction process, you will have a change in oxidation state or charge. So oxidation reduction reactions undergo a change in oxidation states. That is the fundamental identity of those reactions. A reaction such as the metathesis reaction, and we'll show you those today, do not change oxidation states going from reactant side to products. They exchange ions, form precipitants or gases or weak electrolytes. But the compound in the product side will retain the oxidation state that it had in the reactant side. So we have no change in oxidation states for the metathesis reactions. One area that you're going to have to grind out on is assignment of oxidation states. And in the past, I've just presented a lot of equations, and as we go, assign oxidation states, and you begin to get comfortable with putting oxidation states in. And I'm going to continue that process. Two I've given you already. Oxygen, O by O2, or O2 is a zero. That's a molecular form. Oxygen by itself or combined in something is a -2 charge. So if you have sulfate or sulfuric acid or an oxo acid that contains oxygen in it, assume the oxygen is a -2. Now there's one case where you have oxygen bounded directly to oxygen. This is referred to as a peroxide. And in this case, oxygens will be -1s instead of a -2s. So this is a very unique case. The one that you will see, now there are many peroxides, but the only one that I use in the work that we are doing is H2O2. You are familiar with hydrogen peroxide as a disinfectant and whatever you use it for. Hydrazine in combination with the hydroxide. Is rocket fuel. Gives off a lot of energy. Okay, it was used for many years. One of the first jet fuels when Nazi Germany was developing the 262s, Mitsubishi, Mr. Smith 262s. I don't call them Mitsubishi. That's Japanese. The only fuel that was effective was hydrogen peroxide, and they had used a little nitric acid too. Blew up a lot of service people. So I mean, eventually it got to something a little less toxic and a little less explosive. But point is, the oxygen does not always have a -2. Another point is, I will tell you when the case is where it doesn't for right now. If I don't say anything, you assume it to be a -2. Okay? So check mark that in your study. Okay. Composite reaction, I don't know what those are. Standard state reactions, there's no such thing. Metamorphosis reactions, maybe there is, I don't know what it is. But the only one in here that I'm of concern, that is of concern, is the oxidation reduction reaction. Oxidation reduction reactions have a change in oxidation state. Stop me if you'd like to ask a question. I'd be glad to address it if you'd like. When compounds form from reactants, one can always expect. Okay, so I've got reactants, going to products. Can you expect, all right, here are your options. An increase in number of particles. Yes or no? What do you think? What do you think? No. There may be a condensation of elements that, well, H2 plus O2 goes to 2H2O. Now we got two particles over here and two waters, but they may condense down to one. But what is important is that the mass does balance. Well, like A was increase, now B, same thing, decrease in number of particles. Not necessarily. You may have two compounds on the left, two compounds on the right after the reaction's finished. So in dealing with chemical equations, I'm giving you some things that, oh, I already knew all that, just wasting my time. Enjoy the review. Okay? As the reaction goes to completion, you can expect a reaction to experience an energy change. Yes. All reactions experience an energy change. They will go through a process. Now, one thing that you may not be familiar with, you have heard of reactions that start out, lose energy from reactants to products, and we call that an exothermic reaction. In that the energy is lost going from reactants to products. Everybody good on that? You pretty comfortable with that idea? And you are familiar with reactants going to products where it gains energy over the net process. And so this is a gain energy. And that is an endothermic reaction. It's good to put terms that you're going to see in the future down, kind of like planting seeds. And we'll bring these back up later on. Some reaction processes consists of multiple steps, referred to as a reaction mechanism. If you're not familiar with the terminology, a reaction mechanism means that you go through several steps in making compound. You might start with some reactants here and make some products, one here. Then these products will react with something else and then make something else down here, products 2, which then react and make something else, products 3. And then it reacts with something else and winds up with product set 4, which is the objective of the overall process. So it goes through a bunch of steps. As you look at this, and let's assume these were on the same level. Product 4 energy content is on the same level as the reactants before they started reacting. Has that process undergone an energy change? Net energy change equals 0, but it has. You take into account that 0 on the end, or whatever the energy, the total change in energy is the sum of all the delta E's that the process goes through. It just happens to wind up back at the same level. But every process has an energy change. What would we call? We call one that loses energy, exit, loses energy. One that gains energy, endothermic. But what would we call a reaction whose net effect is a 0 change in energy? Anybody know? It's called isothermic. So there's your new word that you may not be familiar with. So in your notes, exothermic process is associated with a net loss of energy, usually in the form of heat. Endothermic is net gain of energy. It winds up the products above the reactant. But don't miss out on isothermic process, which means the net delta energy is equal to 0. And the underlying secrets in here is that going from reactant to products might have gone through several steps, which involve gains and losses of energy. But when we add those gains and losses together, we come out 0. Make sense? Okay, I don't want to make this into a complicated issue. These are terminologies that you will have to deal with as we move through the rest of the text. So there is a term that you may or may not be familiar with. Isothermic. Isobaric is also you'll run into that. That is no pressure change. Okay. I know this is not as Number 4. All of the following elements are diatomic in standard state except Okay, now I gave you a very easy device for identifying those diatomic elements that are quite frequently used. When you look at the periodic table, what do we start with? Say nitrogen, right? Everybody remember what I did? And move to the right to oxygen, and fluorine, and chlorine, bromine, iodine, in that order. And we ask ourselves, what number does that look like? The 7, sure. Now, there are only 6 elements here, 1, 2, 3, 4, 5, 6. Well, where's the 7th? Hydrogen, right. You have to remember hydrogen is also a part of that collection. So hydrogen and nitrogen, oxygen, fluorine, chlorine, bromine, and iodine in standard state are diatomic. And that's the way they should be listed. When included in a molecular equation. Now again, I've mentioned some of the types of equations. You got ionic equations, and we write something like H plus Cl minus goes to HC. You know, that's an ionic equation. That's not standard state stuff. I'm talking about when you have a molecular equation with compounds written in standard state. The point of this question is not just your ability to pick out that, is that a molecular equation that conforms to the laws of chemistry and physics is a standard equation. If I haven't gotten that across to you, then I want to emphasize that right now. If I write, well, N2 gas plus 3H2 gas goes to 2NH3 as a gas. What information can you write down about this equation right now? And I've got a lot more to add to this. We know that the sulfur is not a member of that collection. So I'm going to go ahead and finish this with a D choice right there. But A, B, and C in that collection are diatomic. But what may not have gelled yet in your memory bank is that molecular equations should be written in terms of basic substances in their standard state. Let's write it. Molecular equations are written in terms of basic substances and their standard states. Standard state form of any substance in an equation, written a molecular equation, is generally assumed to be the most abundant form of that substance. The most abundant form of NH3 is ammonia. And where can you go to find out what the standard state formula is for that substance? Where would you go? Don't be shy, guys. I feel like I'm talking to myself half the time. Where would you go? This is a table of thermodynamic quantities. And let's see if I can get that focus a little better. Yeah, it looks a little better. But if you're writing a formula that contains beryllium oxide, it should be written in that form. If you're writing a reaction that contains cyanic acid, it should be written in that form. Because all of them are in this table. These are the most abundant forms of the substances, and they are collections within a thermodynamic quantities table. Now, standard state means what? What does standard state mean? It means that a standard set of conditions has been established for the substances being in standard state, and that's called standard thermodynamic conditions. That's every table that's in the back of the book will be under standard thermodynamic conditions. It's 25 degrees Celsius and 1 atmosphere. Did you know that? Write it down. So if you looked up other issues in this textbook, base ionization constant is going to have out there 25 degrees stuck to it. See the point? Because everything in here is published in terms of the standard states. Another one here. Here's the standard electrode potentials. These are all published based on getting these numbers and results, 25 degrees thing. Now, as we go through the topics that deal with this, you'll learn how to do calculations at standard conditions, and then you'll learn how to do calculations at non-standard conditions. Okay? And you got to know where to start before you can go to at standard to understand how to go to the non-standard. Okay? That kind of issues. Yeah, I'm sorry. Right there, that column right here. Now I'm talking equations and how to make equations and where does stuff come from when you write equations. This is what I'm talking about. But there should be a relative understanding about elements in basic standard state. Compounds, you got to look them up because they'll all have numbers stuck out here, and there's only one, and you're not going to memorize all the numbers, right? That's just ludicrous. But elements in basic standard state are easy to know what their standard heats of formation are. Elements in basic standard state always have a delta H value of what? Anybody? 0. So if I want to know what form oxygen should be when I put it into a chemical equation, I'll look up oxygen in here. And you haven't caught this yet. I come down, look, I've got 1, 2, 3 forms of oxygen. Which one do I use? I look over here under the delta H value up at the top, and I find the one with the 0. That's the standard state of oxygen. If I look over at any element under the delta HF, see, I have another one. That's the standard state of magnesium. In the appendix, you look up delta HF. This is, listen, only for elements, right? It only applies to elements. Come on down here to what's the standard state of manganese? Well, it's a neutral manganese solid. Most common form of that. Mercury. What's the most common form of mercury? It's liquid. How do I know that? It's got a 0 out here. The standard state of elements always have a 0 delta HF. Always have a 0 delta HF. If it is not an element in standard state, it's going to have a number over there that's different. Here's 3 or 4 forms of mercury. Only one of them has a 0. Here's mercury in the gas phase, has a plus 61, 38. Here's some ions of mercury. They have numbers over here. Now the meaning of those numbers and how to use them for whatever is not part of this. What I'm trying to do is teach you about chemical equations and where the symbology comes from and why we choose certain things as we do. Okay? Okay, the last one in here. In a reaction to substances that do not undergo chemical change are referred to as what oxidation states. Do not undergo okay. In a chemical reaction, those substances that do not undergo chemical change are what? Anybody? What are they?
Spectators.
Spectators. They're important parts of the reaction. But in a reaction, substances that do not actually undergo a change are referred to as spectator ions. In an acid-base reaction between hydrochloric acid and sodium hydroxide, the products will be sodium chloride, aqueous, and water in the liquid form. This is a molecular equation, and you write all of the components of the reaction in basic standard format. That is, you look in the back of the book and you get the formula for hydrochloric acid and water, and you write it down, and then you write down the standard state for sodium hydroxide, sodium chloride, and so forth, and balance it with respect to the mass balance, and you have the standard state equation. When you put it together like that. There is a subnote here that you may not know. When taking that equation as the standard state equation, especially when we get to gas laws, you assume that that equation is at STP. What does STP mean? You remember that from earlier courses in talking about gas laws? You don't know? Have you played with STP and gas laws? Is it kind of something way back in the, does it nerve anybody else? STP and gas laws. No, nobody? Come on. Somebody's got a, really? Gas law. Boyle's law? Anybody remember that? Charles law. 25 degrees Celsius and 1 atmosphere. It's a double-edged sword here, depending on what topic you are working in. So when we get to chapter 5 and after the first big exam, we'll be talking about stoichiometry of gas reactions that produce gas phase components. And you have to assume that when you start the calculation from the equation written, it's at 0 degrees and 1 atmosphere. And then you expand or compress from there. They're non-standard. And that's the central objective. In thermodynamics, when you work thermodynamic problems and you're trying to figure out changes in the reaction behavior. You got to start with 25 degrees and 1 atmosphere. Now, we hadn't worked the problem yet. I'm just giving you factoids that you're probably not familiar with. So I'm trying to get you brought up to scale to some more advanced work. So there's some assumptions that you will need to be aware of as we go through this process. Going back to this acid-base reaction, what happens? This is a strong acid, ionizes 100%. Well, I can write that like this, or H3O plus aqueous. This is just an abbreviation of H3O. Protons do not float around in solution by themselves. They kind of attach to something else to go around. But since chemists like me are inherently lazy, we're going to write H plus all the time. Cl minus aqueous plus Na plus aqueous plus OH minus aqueous goes to Na plus chloroaqueous plus Cl minus aqueous plus H2O as a liquid. How do we classify that reaction? Remember what I called it last time? Okay, so acids and bases in water, right here. Ionic compounds ionize. And we'll see when we get to metaphases that some ionic compounds form, they bond so tightly that they will fall out of solution. And those are the ones that pull the reaction to completion and make new substances. Another way to look at a driving force, it prevents the reaction from going in the opposite direction.